Today we will talk about this substance, 3-amino-phthalate hydroside, better known as luminol, whose special property is to emit cold light during a chemical reaction. And we'll show you how to turn that chemical glow off and on like a light bulb. So stay tuned and let's go! Warning: chemical experiments can be dangerous, especially if instructions and safety precautions are ignored. We assume no liability for injury or damage caused by imitating the experiment. Please inform yourself about risks and protective measures and observe the applicable legal regulations when handling chemicals. In order to start the luminous reaction, it needs two components. First, a dilute solution of luminol. Since luminol is insoluble in water and the reaction only takes place in an alkaline environment, the luminol must first be dissolved in a little sodium hydroxide solution and this solution then diluted in water. The second component is a solution of potassium ferricyanide and hydrogen peroxide in water. The peroxide serves as an oxidizing agent for the actual reaction, the ferricyanide primarily as a catalyst that sets the reaction in motion. The exact amounts and concentrations are not critical, even the smallest amounts in very dilute solutions are sufficient. If both solutions are now poured in a flask together, you can see a nice bright bluish glow in the darkened room, but unfortunately this fades relatively quickly. By adding some solid ferricyanide afterwards, the glow can be refreshed a little. This time it isn't quite as strong, but it lasts longer. This shows that the ferricyanide not only acts as a catalyst for the luminol, but, just like the peroxide, also as an oxidizing agent that is consumed in the course of the reaction. At the end of the reaction, a pure catalyst would be exactly as it was at the beginning. However, the ferricyanide, a red salt, is reduced to ferrocyanide, a yellow salt, the iron contained in it from trivalent to bivalent. We've put both salts side by side as solids for comparison. Incidentally, this reduction also occurs as a side reaction under the action of hydrogen peroxide in an alkaline solution. Therefore, the second reaction component is usually used up faster than the luminol, so that the luminous effect can be started again by adding a bit of peroxide or ferricyanide. A nice modification of the luminous reaction is obtained if a spatula tip of fluorescein is also dissolved in the alkaline luminol solution. When the two components are combined, the mixture then lights up green because the chemiluminescence of the luminol excites the fluorescein to its fluorescence. Here you can see an overview of the cause of the chemiluminescence reaction of luminol. You could fill a whole video with a detailed explanation, which is why we don't do it at this point. But in summary, it can be said that luminol is oxidized in alkaline solution by hydrogen peroxide under the catalytic effect of the complex bound trivalent iron and ferricyanide. In addition to nitrogen gas, the luminol also produces a phthalate, which is present as an unstable dianion in the excited state, and returns to its ground state by releasing energy in the form of light. This reaction is not only pretty to look at, but also has practical uses, for example in analytical medicine, where even extremely small amounts of toxins, pathogens, peptides and proteins can be detected with its help. Another area of application is criminalistics. There luminol is used to search for clues, where it can detect even the smallest amounts of blood, because the heme ion it contains is just as catalytically effective as the ferricyanide in our experiment. But now to our initial question. Can this chemical light be switched on and off like a lamp? Let's have a look at two ways to influence the reaction. The first is pH. The reaction only takes place in an alkaline environment. If you now add diluted sulfuric acid while it's lighting up, the lighting stops abruptly. If the acidic solution is then neutralized again with excess sodium hydroxide solution, the glow continues. At least until the catalyst and oxidizing agent have been used up. And that's where the second option comes in, which is much closer to real switching, because we actually have to turn a knob to turn the light on and off. Again we mix our two components, but this time used ferrocyanide with divalent iron. Furthermore, we have set up simple electrolysis equipment, with which we will conduct a direct current of about 9 volts and 1 ampere through the solution. The cathode is on the left and the anode is on the right. If we now switch off the room lights, no glow can be seen as long as no current flows through the mixture. But when we switch on the current, it starts to glow around the anode, because the ferrocyanide is oxidized to ferricyanide or divalent iron and the complex salt to trivalent. which catalyzes the chemiluminescence reaction. In return, water is reduced to hydrogen and hydroxide ions at the cathode. If the power is switched off again, the glow also fades quickly, since the ferricyanide formed is quickly consumed on the spot and fresh ferricyanide is no longer reproduced by anodic oxidation. The process can be repeated until all ferrocyanide, hydrogen peroxide or luminol has been used up. A game that, in contrast to the simple combination of the components, can be played much longer because the reaction area is limited to the immediate vicinity of the anode. The consumption is therefore very economical and can also be controlled by switching on and off and by regulating the current flow. But for this we are now again dependent on electricity actually coming out of the socket. An experiment that fits in well with the times. We hope you enjoyed it. If so, please give us a thumbs up. If you want to see more experiments now, click on our overall playlist at the top right. If you don't want to miss any new videos, leave us a subscription and activate the bell. Thanks for watching, take care and hopefully see you soon. Until then, goodbye!